This is the solution for a question covering the sublearning outcome. Calculate net force on a 2D rigid body using free body diagram and equilibrium equation from Mechanic 1. In this question, there are 4 unknowns, but there are only 3 equilibrium equations, which is impossible to solve this question. Therefore, we need to break the system up. Remember, don't calculate the force equivalence before you break the system up, because if you find the point load first, the point load will only appear on one side of the system after you break it, which is not true. We will break the system up at the pin, which we will name it as point D. Draw all the reaction forces at each point. Point A is a pin support. We will draw the reaction in X and Y direction. Point B and C are both roller support. Therefore, there is only one reaction force acting normal to the surface, which will only react in Y direction. We know point D is a pin, therefore, we will assume that it has both X and Y direction forces. These forces are different than the other forces in the other half of the system, as they're equals in magnitude but opposite in direction. Assume one direction on one side, and make sure to draw the other side that has opposite direction. And it doesn't matter which side you assume up or down. In this question, we will assume the forces on the left side of the system is acting up and to the right, and the right side is acting down and to the left. We will first solve for the system on the left side. Now we can calculate the point load. Negative 2 kilonewtons per meter multiplied by 4 meters, which is equals to negative 8 kilonewton. Negative because it is acting in a downward direction. Then we divide 4 meters by 2, which is equals to 2 meters. We will draw the force in the downward direction on the diagram because the answer we got is negative. We will draw a coordinate system with positive pointing upward and to the right, and positive moments rotating counterclockwise. To find the y reaction at point A, we take the moment about point D that it must equals to 0, which equals negative AY multiplied the perpendicular distance from point D, which is 4 meters. Negative because it is causing a clockwise moment about point D, plus 8 kilonewtons multiplied by 2 meters. Positive because it is causing a counterclockwise moment about point D. Rearrange the equation and we get AY equals to positive 4 kilonewtons. Now we use equilibrium equations to solve for dy, dx, and ax. The net force in y direction must equals to 0, which equals positive dy, positive because we assume it is acting upward, plus negative 8 kilonewtons, negative because it is acting in the downward direction, plus positive ay, which is 4 kilonewtons, positive because it is acting upward. We get dy equals to positive 4 kilonewtons. The net force in x direction must also equals to 0 in equilibrium, which equals positive dx plus positive ax. There are 2 unknowns in these equations, meaning we don't have enough information to solve for dx and ax. We will name this equation E1 and come back when we have more information. Now we can calculate for the right side of the system. First, we will find the point load. Negative 2 kilonewtons per meter multiplied by 2 meters equals to negative 4 kilonewtons. 2 meters divided by 2 is 1 meter. We will first set up an equation to calculate the net force in x direction, which it must equals to 0. We can see that there are no other force in this question that is acting in the x direction other than dx, so we get dx is equals to 0 kilonewton. Recall from the system on the right side, we have an equation E1 that has 2 unknowns. 0 equals dx plus ax. We have found dx which equals to 0. Therefore, we can know that ax is also equals to 0. Now, we have found the reaction at A, which ay is 4 kilonewtons and ax is 0 kilonewton. We have also found the reaction at D, where dy is 4 kilonewtons and dx is 0 kilonewton. We can continue to solve for the vertical reaction at B. Before we start the calculation, don't forget that the set of forces are equals in magnitude but opposite in direction. To calculate the reaction at point B, we will take the moment about point C that is equals to 0, which equals positive 4 kilonewtons multiplied by the perpendicular distance of 7 meters, positive because it is causing a counterclockwise moment about point C, plus positive dy, which is 4 kilonewtons multiplied by 8 meters. It is positive because it is causing a counterclockwise moment about point C, plus negative by multiplied by 6 meters, negative because it is causing a clockwise moment about point C. Arrange the equation. We will get by is equals to 10 kilonewtons. In this question, we have identified the support at point A, B, and C. There are pin support, roller support, and roller support. We have also found the reaction at point A, B, and D by breaking the system up, which AY is 4 kilonewton, AX is 0 kilonewton, DY is 4 kilonewton, DX is 0 kilonewton, and BY is 10 kilonewton. Remember, don't calculate the point load before breaking the system. It is not true. And remember, the forces are equal in magnitude but opposite in direction when you break the system up.